Welcome, my friends, to our discussion on stoichiometry. Today we're going to be talking about how to use balanced chemical equations to predict the amount of reactants and or products that we can make from a chemical reaction. We're going to really push today to try to understand what each number means as we go through this process. So let's get going. So we have this balanced equation for the burning of butane. So we have butane here on the left, which is C4H10. And we're going to react it with oxygen, and we're going to burn it, and we're going to make carbon dioxide and water. So here's our carbon dioxide and our water here. Now, what stoichiometry lets us do is it lets us be able to predict how much oxygen we need, how much butane we need, how much carbon dioxide we'll make, and how much water we'll make. So let's get after it. The first thing we do is we're going to read this thing. We're going to say, hey, how many grams of oxygen? So we're trying to figure out this, right? So here's our unknown that we're trying to get to. Are needed to burn 13.56 of butane. So we know this amount, and we know this amount is 13.56 grams of butane. And we're trying to take that and go over here to oxygen and figure out how much of this we need. Now we know that for every 2 of these, we need 13 of these, and that we're going to make 8 carbon dioxides and 10 waters. So, but we can't really use that number yet because this number, 13.56, doesn't tell us how many CH4 or butanes we have. It tells us how heavy the sample is. So we got to first turn this how heavy number into a how many number, into moles. So then we can say, okay, for every 2 moles of this, we need 13 moles of this. Then we can use our equation. So the first step then is to start here with butane. So 13.56 grams of butane. And you need to keep track of what the units mean. So the grams, you have to have the grams for sure. And you have to have the butane as well so you know which grams it is. And here I put butane. I could have put C4H10, but I chose to write butane. Now we need to turn this how heavy number into a how many number. And to do that, we're going to use the molar mass. And we get that from the P table, the periodic table of the elements. So when we look over here, we get butane. We know that there are 4 carbons. So we do 4 times the mass of carbon plus 10 times the mass of hydrogen. And what we get from that is 58.12 grams per mole. So each mole of butane has a mass of 58.12 grams. Now we can tell we have 13.56 grams of butane. And because 1 mole is 58.2, we must have less than a mole here. But let's do that work real quick. Now we want to cancel grams. So this gram is on top right here. The next one has to go on bottom down here. So I'm going to put grams of butane down here. And that means my moles of butane are going to go up here. And then I got to figure out what numbers go here. So I look at my molar mass. I'm like 58.2 grams per 1 mole. So the 1 goes with the mole, and the 58.12 goes with the grams. Now I have my grams canceling, and my first step is complete. But I need to figure out what this first step means. So from here back this way, all of this stuff here, if I would do the math right now, these first 2 things, or this divided by that, this tells us the number of moles. I know that because it says moles of butane, that's what's left. Moles of butane that are in 13.56 grams of butane. That's what this number means so far. So now we know how many moles of butane are in this much butane, 13.56 grams. Now being able to make this statement, this is the real chemistry of it. Anyone can set it up so that units cancel. But really understanding what the number means is what we're really pushing for. So each step you're going to be writing down and pushing for understanding what that number means. It's going to help you so much in the future if you understand what you're doing. All right, so now this tells me how many butanes, the number of moles of butane I have. And I know from the chemical equation then that for every 2 of these, 2 moles of these, I need 13 oxygens. So now I'm going to use my balanced chemical equation to do the next step. And I have moles of butane up top here, so I want to put moles of butane on bottom here. Moles of butane, so they cancel. And I'm going to moles of oxygen. So I'm going to put moles of oxygen on top. And I know they had to cancel there. And all I have to do is look up here. I go, okay, for every 2 of these, I need 13 of these. So every 2 butanes, I need 13 oxygens. And again, I knew to put butane on bottom because butane was on top here. So now they cancel out. All right, so now we have to ask ourselves, well, what does this number mean after each step? So from this point over, what does this number mean? And what it means here, it's the number of moles of oxygen that you need in order to use up 13.56 grams of butane. Let's write that down. Number of moles of oxygen you need to use up 13.56 grams of butane. Notice how our language has changed. Here, this many moles is in that many grams, so we used in here. This one, oxygen's not in the butane, so we can't use that language anymore. This oxygen is something separate. It's not in the butane. It's what you need in order to use up this amount. That's super cool. Like we just predicted how many moles of oxygen we need to use up that much butane. 13.56 grams, I should say. That's super cool. All right, so now the last thing you have to do, now it would be cool, we're actually pretty much done here. We know how much oxygen we need. The problem is, in the lab, we can't go out and count moles. We don't have super tiny tweezers to pull out 13 moles of oxygen, and if you did, you'd be counting forever, because it's a huge number of stuff. So we need to convert this moles back into grams now. But this time we're going into grams of O2. So I know my moles of O2 are on top. Oh, and this, let me write up here that this is the ratio from the equation. From the chemical equation, right? And now we're going to use the molar mass again. But this time we're going to use the molar mass of oxygen because we're switching oxygen to grams. And then we're going to, so we know the moles go here of oxygen. And that means the grams must go on top. And we can look in the periodic table and the mass of oxygen is 16. So O2 must be 2 times that. So it's 32.00 grams per mole. All right. So now we're looking at 32.00 grams in 1 mole. Notice here moles of oxygen cancel and we're left with just grams of oxygen. Let's do the math real quick and then we'll explain what the number means. So on this math, we always start with our first number. Just type it in, 13.56. Now this next number is on the bottom of the fraction. So we're going to put divide before it. So it's going to be divided by 58.12. This next number, the 13, is on top. So we hit times 13. This one's on bottom, so we hit divided by 2. This one's on top, so we hit times 32. And we end up with an answer of 48.53 grams, and it's O2, grams of O2. So what does this number mean now? This means you need 48.53 grams of oxygen to use up, and maybe you can even use the word burn here, to burn 13.56 grams of butane. Now that's stoichiometry, and that is absolutely gorgeous. So just by having this balanced chemical equation and some molar masses from the periodic table, you can figure out if you have this much butane, how much oxygen you need. If you have 13.56 grams of butane, you need 48.53 grams of oxygen to use it up. That's cool. All right. That's the first one. Now remember, if you can't do the explanations, you're not there yet. Keep working hard at it. All right. Let's do another practice one. This is fun. So we have the same equation still. We still have butane with oxygen making carbon dioxide and water. But this time we're like, well, if we burn that same 13.56 grams, we know we need 48 point whatever grams of oxygen. But how much carbon dioxide will we make? So we're going to start here. with 56 grams. And now instead of going to oxygen, we're going all the way over here to carbon dioxide. And we're saying, how many grams of carbon dioxide will we produce? All right, let's get after it. So it's going to start in the exact same way as before. 13.56 grams of butane. You know, maybe I'll do C4H10 this time, just to show you that that's possible. And now I need to convert that into, from a how heavy number into a how many number, so then I can use my chemical equation. Because for every 2 of these, I make 8 of those. So I go here back to my 58.12 grams. And I got that number from the periodic table. All I did was add up the mass of carbon times 4, hydrogen times 10. That gave me 58.12. And then that's 1 mole of C4H10. So now this number cancels. Again, we got to push ourselves to understand what this means. What does all this mean so far? So of course, this is the number of moles of C4H10 in 13.56 grams. So this tells us the number of moles C4H10 in 13.56 grams of C4H10 butane. All right. So now we know how many butanes we have. We have this number of moles of butane. So now we can use our how many numbers from the periodic table or from the chemical equation to be able to solve. So here we have 2 moles of C4H10. And you might be saying, well, how did you put that on bottom? And it's because it's on top here. So it has to cancel, so it has to go on bottom of the next fraction. And then this next one is 8 moles of CO2, because that's where I'm going. I'm going to go to CO2. All right, that's that next step. So moles of C4H10 cancel out. Now the question is, what does this number mean? So from this point over, all 3 of these things together, this tells me the moles of CO2, and because it's a product over here, I'm going to change my language. I'm going to say this is the number of moles of CO2 that will be made if you burn 13.56 grams. Notice how my explanation always comes back to my starting number. So this is the number of moles of CO2, that will be made if you use, or maybe even just use the word burn, if you burn 13.56 grams of the methane, C4H10. Notice how my language has changed here as well. In the previous problem, we were saying how much oxygen we need to use up because it was a reactant. Now that we're in a product, it's like how much stuff we're making if we use it up. So be careful with that, how else to make sense. Now our next step, we have moles of CO2, but we need to convert them to something measurable in the lab. So we need to convert from moles, the how many number, into how heavy. So we'll do the moles. We'll have 1 mole of CO2 on bottom. And I know that the mole of CO2 goes on bottom because it's on top here. And when I look at the periodic table, I can figure out that this has a mass of 44.01 grams per mole. And so that's where the 44.01 grams of CO2 for every 1 mole. Grams go on top, moles go on bottom. That way moles here cancel moles here. And in the end, I get this final number. So again, we start by typing our first number in, 13.56. Our next number is on bottom, so it's divided by 58.12. The next number is on top, so we do times 8, divided by 2. The next number is on top, so we do times 44.01. And we get an answer of 41.07. And I know I start with 4 digits, 1, 2, 3, 4, 4 significant figures. So I want to end with 4 as well, 1, 2, 3, 4. And that's why I've chosen to round to that 7 right there. All right, and what's left? Grams of CO2. Okay, so now what does this number mean? Well, this means you will make 41.07 grams of CO2 if you burn 13.56 grams of butane. Fantastic. This is a beautiful answer. Now we can even check to make sure this makes sense. Now notice that carbon is only part of this methane, so it's only part of this 13.56 grams. So you might be saying, well, gosh, how does it get so much heavier? Because 13.56 grams makes a heavy mass of CO2. But then you recognize that, oh, so the carbon is here, but it also has 2 oxygens from here. So the mass should be greater in the end of what we got for our products. So that answer does make sense. All right, let's try one more because this is fantastically cool. Now this last one, we're going to do a different route. So we're going to say, hey, we need to make 56.25 grams of water. And we want to go over here, we want to go this way now. We want to go backwards and say, how many grams of butane do I need to burn if I'm making water? Now, admittedly, this is a really dumb way to make water, but you could do it. I mean, it's possible. You could make drinkable, delicious water by burning butane and collecting the gas off the top of it. It would be containing all kinds of great water. All right, so the difference on this problem is that we're starting with a product and we're going back to a reactant. And then the process is exactly the same, except we'll just be going in a different direction. And we have to do a different interpretation. So let's get started. We start here with our 56.25 grams. 56.25 grams of H2O. Now again, before we can use this 10 and 2, we've got to convert from a how heavy number to a how many number. So we need to convert this grams into moles. So when I look in the periodic table, I add up 2 hydrogens plus an oxygen, and I get 18.01 grams of water is equal to 1 mole. Now again, I knew to put the grams on bottom because grams are on top here, so they'll cancel out now. All right, so the next question we ask ourselves is, what does this number mean? So I go like this, and I go, okay, so this number here, it must mean this is the number of moles of water in 56.25 grams of water. So this is the number of moles of H2O in 56.25 grams of H2O. So basically we've just converted our how heavy into how many. And now because we have the how many number, we can use our chemical equation to see that for every 10 of these I want to make, I need to have 2 of those. I need to react 2 of those. So, and I know my moles of water are on top here, so the next mole of water has to go on bottom. So the 10 moles of water go on bottom. And the 2 moles of butane go on top, because that's where I'm headed. I want to know how many butanes there are. And I'm going to do the C4H10 again. Okay. Now the moles of water cancel out. Okay, so this question begs, well, what does this number mean now? If we stop right here and do the math, what would that number tell us? That number would tell us the number of moles of C4H10 you need to burn in order to make 56.25 grams. Notice how our language has changed again. Now we're starting here, so we're like, okay, so we need to use up this in order to make that. So this tells us the number of moles of C4H10 we need to react. I could use words like use or burn here as well. So all these words work great. Need to react to make 56.25 grams of water. All right, now again, our last step. We know how many moles of butane we need, but we can't really measure moles in the lab, so we need to convert that to grams, something we can measure. So we're going to use our molar mass to do that with. And remember, the molar mass of butane is 58.12 grams per mole. All right, so I know my moles of butane are on top here, so the moles this time have to be on bottom. So my moles of C4H10 on bottom, which means my grams of C4H10 are on top. And there are 58.12 grams. So 58.12 grams in 1 mole. And now he's got to find the answer. So again here we start with 56.25, our starting number right here. And then this number's on bottom, so we divide. Divided by 18.01. The 2 is on top, so we do times 2. The 10's on bottom, so we do divided by 10. And then the 58.12 is on top, so we do times 58.12. And we get an answer of 36.30. Again, I'm looking to have 4 significant figures, or 4 digits, because there are 4 in my starting number. And, oops, sorry, moles of butane should have canceled. Grams of C4H10. Now, of course, the final question we have to answer is, well, what does this number mean? And this number means in order to get, or you need to burn 36.30 grams of C4H10 in order to get 56.25 grams of water. So you need to burn, and here the words react or use would work as well, 36.30 grams of butane in order to make 56.25 grams of water. Now you can word this any way you want. You could have said, in order to make 56.25 grams of water, you need to burn 36.3 grams of butane. It's totally fine as long as you have the meaning of those numbers clear. And those meanings just change depending on what you're doing. So you have to always be thinking about, what does the number mean? Because in chemistry, a number without meaning is, well, obviously it's meaningless. So I hope you enjoyed that little mini lecture. If you need more help, come see me in class. Have a good day, my friends.